This is Jerry Van Develde. I'm going to be your presenter for this afternoon session on foundation engineering. First of all, we have a table of contents just so for your easy reference in studying in the future. These are the primary topics that we're going to be talking about this afternoon. Again, reference to the website for the National Council of Examiners for Engineering and Surveying. If you haven't been to that website, you certainly need to go to it and spend a little time looking around just so you can have a good understanding of the exam requirements in terms of what you can bring, what you can't, and the contents and so on and so forth. There's a good 30 or 40 minutes worth of information in there that is worth looking at, and you should do it early in your studies. So I highly encourage you to do that. References for this session are really the same as were presented on Tuesday. I try to keep that to the minimum since books are expensive and you have a limited amount of time to become familiar with them if you don't already have them. These, again, are classic references here, widely available in new or used form in most cases. I think all these are still in print in some fashion, in some edition. And again, the NAVFAC manual can be downloaded either in its entirety or in parts off the web. Just search for that, and you shouldn't have any trouble. And there's lots of information, great information available out on the web. But again, I caution you, don't spread yourself too thin. It's better to know one or two references really well than to have so many that it takes you a lot of time to find what you're looking for. So pick some good ones, become familiar with them, and use them in your preparation. And as far as success in the exam, it's all about doing the problems and going through the material. So develop a discipline to study a little bit at least 3 or 4 times a week and get going on that earlier so you have time. The more time you spend doing the problems and working through the information, the better you're going to do. All right, first topic this afternoon is foundation type in terms of how you know what type of foundation to use. In general, the type of foundation system that you want to use is going to be controlled by the load capacity that's dictated by your design. But it would also be dictated to some degree by the performance of the foundation. You can have, say, shallow foundations that might have the load capacity, but they may have excessive settlement that would limit their usability on certain types of structures, particularly if the structure is very sensitive. And of course, it's not all just controlled by the vertical downward loading in the foundation. Sometimes you have limitations of lateral loads or for that matter, uplift loads, particularly in this day and time where there's more and more focus on wind loads and seismic loading in the building code requirements. And with the stiffening elements that are required to resist some of those types of loads, you end up with a lot of uplift loads that we see situations in certain types of soil environments where the uplift capacity is just not available without going to great extremes with shallow foundations. So in some cases, you might have to look to some other type. Now, in terms of something beyond a simple footing, certainly a mat or a raft, a mat being a very broad type of area, just a uniform pad that the entire building or at least a large portion of the building would sit on could be a mat for a machine foundation. Raft is a very similar sort of thing. Raft gets used in a lot of different ways. A raft can be a combination of several footings in an area, or in some cases a raft is more of a displacement type mat, meaning that the raft is put down at a depth where the material you're removing is roughly equivalent to the bearing pressure that you're going to apply. So those terms are somewhat similar and the concepts are somewhat similar between mat and raft. If you need capacity beyond that, whether it's uplift, lateral loads, or downward loading, then in a lot of cases you might want to look at deep foundations. Deep foundations can consist of many types of piles. There are driven piles and augured piles and extruded piles and all kinds of piles made out of different materials and installed in different systems. And then there's drilled piers, sometimes called caissons. The big difference between, say, an augured pile and a drilled pier in general is that usually somewhere in the drilled pier process, the material within um, the annulus, so the void that is created, that is going to constitute the cross-section of the pier. Generally speaking, in drilled piers, that soil is removed, and even though there may be a temporary casing in there, you do have an open void, an open volume at some point during the installation process. And that may be filled with water, may be filled with drilling fluids, but in general, material is drilled out using an auger of whatever size is appropriate for the cross-section of the pier. And then concrete is placed statically from the bottom to the top usually. Um, and, um, and so that is what creates the drilled pier. And in other situations where you have an augered pile, say for example, usually that void never exist in its entirety. The auger is screwed into the ground with, in a lot of cases, a minimal amount of removal of the soil, and then the grout is injected at fairly high pressures, and that installation of both screwing the auger in and then injecting grout at high pressures actually densifies and makes a much more intimate contact. So as you'll see later on as we go through the design analysis, there's a little higher coefficient of interface friction assigned when you don't have an open annulus at some point where the soil can start to kind of relax into that and demobilize some of the confinement. So we'll look at that more as we go forward. And again, another thing that's different between a drilled pier or a caisson and an augered pile or a driven pile is usually drilled piers are limited in depth to about 100 feet. Many years ago when drilled pier installation was done by lowering people in caissons or holes, drilled pier holes. I've been in drilled piers over 120 feet deep, but generally speaking, about 100 feet starts to be the limit. They make equipment that goes deeper than that, but you don't see it used very often, whereas piles can go down to 150, 180, 200 feet, heaven forbid, if the conditions warrant that. Okay. And then, of course, there's all kinds of other types of systems that could be used in terms of ground improvement, micro piles and helical piles and all kinds of other systems that could be used, again, that might be considered, stone columns could be considered more of a ground improvement than a specific foundation element. But you just have to work through the options until you get a combination of both capacity and performance criteria that satisfies your needs. First type of foundation we're going to talk about this afternoon is a simple footing, and we're going to talk about how we would go about determining the bearing capacity of a footing or of the soil, and then of course the size of the footing that would have to be designed based on that bearing capacity. So what you're looking at here is an illustration of a two-dimensional analysis of bearing capacity that actually was originally developed. The equations related to that logarithmic spiral type failure plane within the straight legs coming up past the bearing surface as you see there. That design of that analysis was originally developed by a researcher named Prandtl. And those equations were derived in general, and then that was converted into English by Terzaghi, and then through Terzaghi and Meyerhoff's research, coefficients and relationships were modified somewhat until you see the version as it exists here. But that's the basic general bearing capacity design equation that you most commonly see, and that is the failure mode. It is a symmetrical failure where you have displacement out both sides. And where you might see something like this as an illustration of a symmetrical bearing capacity failure, a good example might be, for example, a wheel rut, where you have a wheel that runs across soft ground, and because the wheel is rigidly held and can't rotate one side or the other, in some cases, not always, but in a lot of cases, you get displacement out both sides. So there's an illustration of when you might have something like this. When a full-size foundation like a mat or something fails, you typically don't get symmetrical failure. Most of the silos that you see fail. They fall over one side or the other just because of eccentricity in loading and non-uniformity in the soils and so on and so forth. So this is an illustration of the ideal conditions, but clearly in practice things could happen a little bit differently. All right. So we're going to talk about the values that go into this equation, but just recognize what we're looking at here. This is the foundation, and of course this is the bearing pressure. This is the bearing surface, and this up here is the ground surface. So we have some confinement that is created that helps bearing capacity by virtue of this depth, d sub f, from the ground surface down to the bearing surface, okay? All right. Now, there's several types of bearing capacity we can talk about in terms of what language we use or what questions could be asked. And so the very basic type of bearing capacity would be the ultimate bearing capacity, which is based on this complete failure of the shear strength of the soil. And so that is the maximum load or pressure, actually, that can be applied at the bearing surface before you get bearing capacity failure. So that's the ultimate value. Then, of course, if you divide that by a factor of safety, then that would be an allowable bearing capacity. Now, very commonly when we are doing design, we don't design based on the allowable bearing capacity. We do our design based on the allowable net bearing capacity. And what do we mean by the net bearing capacity? Well, the net bearing capacity is simply the ultimate bearing capacity minus the weight of the foundation and any soil that's sitting directly on top of the foundation. And we do that because in a lot of cases the structural engineers want to know what load can they put down here at this surface because that's just convention for the way the responsibilities are typically shared. So usually the structural engineers are looking for that value, so that's the language. But it is important to pay attention to A, what you calculate, and B, for the purpose of the exam, what questions are you being asked? And so you have to make sure that you pay attention to if somebody is asking for the ultimate bearing capacity, the net bearing capacity, or the net allowable bearing capacity, okay? And again, the factor of safety that we would apply when we're going from ultimate or net to allowable net would typically be something in the range of 2 to 3. In the absence of a statement in the exam telling you what factor of safety to assume, in most cases you would assume a factor of safety of 3 for bearing capacity, okay? All right. So again, this is just showing us that the net allowable or the net bearing capacity here at the bearing surface is going to be the ultimate capacity as illustrated by this equation minus the weight of the foundation and the soil above it. So that's that correction of the minus part that's been added on to this equation. All right, let's start talking about the bearing capacity equation itself. So there are 3 bearing capacity factors. They all start with N. So we have N sub gamma, we have N sub C, and we have N sub Q. Okay? N sub gamma is the bearing capacity factor that takes into account the shear strength along this section of the bearing capacity failure that stems from the friction along that shear plane. Okay? This is the only part of the bearing capacity equation that takes into account the width of the foundation. It's the only place it shows up. And again, the N sub gamma takes into account primarily the frictional components of the bearing capacity. Okay, so the value clearly is going to be affected by what our friction angle is, phi. If we have a friction angle equal to 0, then N sub gamma is going to go down and be 1. Now, one thing the bearing capacity equation tells us is that we have to start off assuming a foundation width. We have to assume this general bearing capacity equation assumes an infinitely long foundation into the page or into the screen. But we have to assume the foundation width. And if you don't know what it's likely to be, you just have to pick something reasonable. Now, for the purpose of the exam, they may tell you something or just use your judgment. Pick 2 or 3 feet if they don't tell you otherwise. And if when you get the answer, it looks like the footing needs to be a lot bigger, then you got to go back and plug that in and adjust your numbers slightly. All right, we got a question here. Didn't get N sub gamma. N sub gamma is a bearing capacity factor. I'm going to show you a chart in a minute where that comes from, but it just represents the bearing capacity that stems from friction along the shear plane. Okay. All right. Now, N sub C is the bearing capacity factor that takes into account the cohesive strength, the shear strength related to the cohesion along the bearing shear plane. Okay, so that takes into account any cohesion that you have. And again, it does depend somewhat on the friction angle in terms of the value that you're going to see in the chart in a few minutes. But if the friction angle is 0, in other words, you don't really have any, it's a undrained condition, or it's a phi equals 0 type soil like a real plastic clay or something, then the N sub C bearing capacity factor drops down to about 5.3. There's actually some dispute on exactly what that value is, but for the purpose of the exam, that's a typical range, or that's a typical value that you might see. And you'll see again on the chart where that comes from. N sub Q is the last of the bearing capacity factors, and N sub Q takes into account the bearing capacity that you're going to get by virtue of the surcharge, and that is the soil that exists above the bearing surface. So here's the bearing surface here where the footing sits, and this is the ground surface. So Q, which is the surcharge magnitude, is just simply going to be D sub F times the unit weight of that soil, the unit weight of the soil above the bearing surface. Okay, so that's just the shear strength you're going to get, or the bearing capacity you're going to get, rather, based on the confinement created by the surcharge on the sides of the foundations. Okay, got a couple more questions here. Will phi be given? Yeah, in most cases, they got to tell you what the soil is like, and we're going to work through some examples so you'll see what you do when they don't tell you that. But yeah, in general, you're going to be given the properties of the soil, the friction angle, the cohesion, because there's no way for you to know that if you're not given some data. Friction angle in this problem is 45. No, good question. That's not the friction angle. That is simply the angle of incidence that this shear plane makes with the horizontal plane as this failure surface comes out of the ground. As you get this logarithmic spiral along from the center of the footing and then symmetrically along outward from the base. But basically, once you hit the bearing elevation, then the shear plane is just simply a 45-degree angle off the horizontal. Okay, so that's not the friction angle. All right, quick question here. Is bearing line B to B? Let's see, yeah. The bearing line is B to B. It's also A to A prime. Let's see, the question is, or along C dash C. I'm not seeing where C dash C is. No. Okay, C dash C is down here. No, the C to C prime, this is the failure plane, okay? This is the failure plane, okay? A to A prime is the bearing surface of that foundation, and so that is the bottom of the footing, and so that is the bearing line, okay? But this from O down along these curves to C prime, or in the opposite direction from O over towards C, that is the failure plane. Okay, that is the physically kind of like a slope failure. You have this nice, in a cohesive soil, you have this nice circular failure plane. It's the same kind of phenomenon that drives this. And why does it do that? Well, it does that because in a friction soil, the shear strength of the soil increases with depth. Why does it increase with depth? Well, because you have friction and you have more confinement, therefore the shear strength is going to go up. So it really can't plunge downward into the soil because as you go down, the bearing capacity will get higher and higher, right? So it's going to develop a shear plane and fail upward and outward in accordance with this design theory, okay? All right, so what is the friction angle then? We don't know yet. Nobody's told us that, okay? So just hold on for just a second. Let's finish this illustration, and we're going to get to that. All right, I already talked about that D sub F is just the depth of the footing for the purposes of the correction of the net conditions. All right, so again, this is theory is for an infinitely long foundation. Here is a typical bearing capacity chart. You can get these off tables. There's dozens of different researchers with dozens of different charts. Don't worry about it. Use whichever chart is in the reference that you have. The answers that they're going to be available to you on the exam are going to take into account the range of typical values that you would use, whether you use Meyerhoff's curve or Bell's curve or somebody else's curve, unless they give you the data. They may very well give you the bearing capacity table or chart and tell you to use that one, and by all means use that if that's the case. All right, so what are we looking at here? Here on the vertical axis is the bearing capacity factors, and those are presented, and that's a log, or that's a log scale there. And then along the bottom, we have three different plots, basically. The first plot from 0 to 40 degrees is for n sub gamma, and these are just side-by-side plots. There's no reason for them to be connected like this, other than it's just a convenient way to do it, rather. And then the second plot from friction angle of 0 to 40 degrees is for n sub c. And again, remember, if you go down to the base line and the friction angle is equal to 0, n sub c drops down to about 5.3. It doesn't go all the way down to 1 like the other two do. And then for n sub q over here, again, 0 to 40 or even 45 degrees. I guess really they're all 45 degrees because 45 degrees would be coincident with a 0 on this scale. But anyway, friction angle along the bottom, and then the bearing capacity factors as shown there. Now, there's one other thing you need to be aware of. That's sensitive local failure. Sensitive local failure is not a magic mystery thing. It just basically means that you got a situation where, for one reason or another, the shear strength doesn't necessarily increase with the depth because you've got an unusual set of conditions. And so when would you use that? Well, for the purpose of the exam, you would use that if they tell you that you have a sensitive soil or you've got a foundation that experiences local failure. And what's an illustration of what that would look like? Well, that would be very similar to what you would have if you just develop a cone of soil, a wedge-shaped cone of soil under the bottom of the footing, and then that's just driven into the ground or pushed into the ground progressively, similar to like driving a post or a pile in the ground. Even though the bottom of the pile of the post is blunt, is flat, in reality what happens is you develop a wedge of compacted soil under the bottom of that. It looks kind of like a nail point or something, a bullet head. And then you just shove that progressively into the ground, and it just simply displaces the material outward because, for whatever reason, the shear strength really isn't increasing very much with depth. So use the general bearing capacity factors by either Meyerhoff or Bell unless they tell you that you have a sensitive soil or you have a local failure. Okay. All right, now the bearing capacity factors as shown there were for infinitely long foundations. But if you have another shape, if you have a square footing or you have a rectangular footing or if you have a circular footing, then you have to correct the n sub c for cohesion and the n sub gamma for the friction, shear strength. There is no correction for confinement. And these are the coefficients that you would apply for each of those conditions. Okay? Again, the general bearing capacity factors that you saw on the chart back here, these are for infinitely long foundations, into the page. But say, for all practical purposes, a wall foundation. But if you have a column foundation, square, let's say, then you have to apply factors. All right, I have a question here. How do you determine the bearing capacity factor? Okay, you determine the bearing capacity factor by knowing the friction angle. Okay, let's just say we have a 30-degree friction angle. Then our bearing capacity factor, we're going to go up, and let's just use Meyerhoff's chart. We're going to follow 30 degrees up until Meyerhoff's curve here crosses a 30-degree line. Then you're going to look over for the bearing capacity factor, and you're going to see it looks like it's about, what is that, 15. Okay, and that's the n sub gamma. And for 30 on the n sub c, again, we would follow that up using Meyerhoff until we get to cross the curve there, and we'd see n sub c has a bearing capacity factor of 30. And then the same thing for n sub q. Okay, good question. Yeah, we just pull it right off the chart. Or, and again, you could pull it off a table or something else. All right, Matthew, let's see here. What is the difference between Meyerhoff and Bell? Just a little difference in research, and that's one of the things that you just have to accept about geotechnical engineering is there's still lots of different theories about how some of these things really equate and how the failure surfaces are really configured. So there are variations. And again, don't worry about it. Use whichever one you like. Maybe you like Bell, maybe you like Meyerhoff, maybe you like somebody else. Unless on the exam they tell you which one to use or they give you the chart, whichever one you use should be fine. You're not going to get that big of a difference. It's not as if Meyerhoff is going to give you 5,000 pounds per square foot and Bell is going to give you 2,000. They're going to be relatively close by the time they all roll into to the equation. And so the answers that are available to you should compensate for the fact that there's some variability. They probably would just tell you which one to use or they'll give you a value. So don't sweat that. Okay, will the angle of internal friction be given? Yeah, if there is one, it would be given. Now, if they say, there is no angle of internal friction, then the assumption is that it's zero, right? And so N sub Q and N sub gamma are going to both go to 1, and of course N sub C is going to go to 5.3 or thereabouts, okay? Yeah, no problem there. All right, so let's work through a problem. I think once you work through this, some of these questions will resolve themselves. Now, we have a simple footing. It is a square footing, interior square, column footing, let's say. We're going to put 75 kips of dead load and 50 kips of live load. The soil has a moist unit weight of 120 pounds per cubic foot. The soil has an unconfined strength, Q sub U of 1.8 KSF. Notice that the groundwater is at the bearing surface. The footing is going to be about a foot thick. We're going to have a foot of soil between the top of the footing and the bottom of the floor slab, and the floor slab itself is 6 inches or half a foot thick. And the question is, what's the allowable bearing capacity of this soil? Okay. All right. So we're going to calculate our allowable bearing capacity. In this case, as you can see, we're assuming that and be very careful with this. They ask what the allowable bearing capacity is, but they didn't say the allowable net bearing capacity. So for the purpose of the exam, if they didn't say allowable net, I would not put the net correction in there. I would just use the ultimate divided by the factor of safety. In most cases, they're going to say what is the net allowable or what is the ultimate value, those two. But just be careful and pay attention to what they're asking. All right, so here is the general bearing capacity equation divided by the factor of safety. Now, since the friction angle is equal to 0, we know that N sub gamma and N sub Q are both going to go to 1. We know that from our previous discussion. Now, how do we know the friction angle is equal to 0? Well, there's 2 hints here. Number one, nowhere in the data they gave us do they mention the friction angle, so we have no choice but to assume that the friction angle is 0. The other thing is they are defining the shear strength of the soil based on an unconfined strength, which is an undrained test, and the unconfined strength doesn't take into account various confining pressures, so there's no way to define the friction angle since it's only one test run at one confining stress, and again, the confining stress is 0, hence the name unconfined. So the assumption normally is if the shear strength is specified by virtue of the unconfined strength, then the friction angle is equal to 0, okay? All right, so let's just start putting in the information that we know. Now, one thing we don't know, come to think of it, is the width of the foundation. So we're just going to look at it, and we're just going to say, let's just pick a number. We're just going to pull something out of the air, let's say, and let's just say that we're going to assume the width of the footing is 7.9 feet. Clearly, we might have rounded it off to 8 feet, or maybe we assume 3. It doesn't really matter for these purposes. We don't know, so we're just going to pick a number. So we're going to pick 7.9 feet. Okay. Now, we know that we're going to have a cohesive shear strength element because we've been given the shear strength in terms of unconfined strength. So we know N sub C is going to be a factor. We know the friction angle is equal to 0, so N sub C is going to be 5.3. Since it's a square footing, is what we were told, that we know we're going to have to apply shape factors for N sub C, and that shape factor is 1.25. Came right off the chart. We looked at it a few minutes ago. For N sub gamma, since the friction angle is equal to 0, then N sub gamma is going to be equal to 1. The shape factor for N sub gamma for a square footing is 0.85. For N sub Q, since friction angle is equal to 0, that's going to be equal to 1, and there is no shape factor for the surcharge element of the bearing capacity, okay? That's that value right there. All right, so let's just plug all the numbers in here. Starting over here on the left side, that is the shape factor. 1/2 is part of the equation. Now, here's something interesting. You need to pay attention to this. We were given the moist unit weight is 120 pounds per cubic foot. We have to assume, since we're not giving any other data, that the moist unit weight is equivalent to the saturated unit weight. We know that this failure plane down here below the footing that is the general bearing capacity portion of it. We know that's under that shear plane, logarithmic spiral curve is down under the footing, and therefore we know that the unit weight of the soil from that component of the bearing capacity is in a submerged condition. So we have to use the submerged unit weight. We're not going to get the full benefit of the moist unit weight, and the submerged unit weight is equal to the saturated unit weight minus the unit weight of water, which we're going to just claim as 62.4 based on the temperature of the water and so on and so forth. Okay, 7.9 is the width of the foundation that we assumed, and then 1 is the N sub gamma bearing capacity factor for a friction angle equal to 0. Okay. All right, now for our next bearing capacity element, 1.25 is the shape factor for N sub C. 900 is the shear strength of the soil, cohesion. Now, how do we know that's true? Well, we were given the shear strength of the soil in terms of unconfined strength of 1.8 KSF, and we know since unconfined strength Q sub U, that is the diameter of the Mohr circle from the confinement of 0 out to the maximum load applied or maximum stress applied to the specimen was 1.8 KSF. We know that the shear strength is the radius of the Mohr circle, so that would be half of the unconfined strength. So cohesion is always 1/2 of the unconfined strength. So 1.8 KSF divided by 2 is going to tell us we got 900 PSF as our cohesion. Okay, so that's where that comes from. 5.3 is the N sub C bearing capacity factor. All right, then we move on. Now we have shear strength related to the surcharge, and that's any weight that's above the bearing capacity, or excuse me, the bearing line, okay? So we have 2.5 feet of material. That's a foot for the width of the height of the foundation. That's a foot of soil above the foundation and below the floor slab, and the thickness of the floor slab is 1/2 foot, okay? So we have 2.5 feet of material, and we're just going to say all that stuff weighs about 120 pounds per cubic foot. Clearly, we could break it down into concrete and soil, but just for simplicity, we're going to say it's 120. The 1 is our N sub Q bearing capacity factor based on the friction angle equal to 0. Now, we also go to, since this is a net bearing capacity equation, we're going to subtract the weight of the foundation and any soil sitting on top of it. So again, that dimension is still the same. The footing's a foot thick. There's a foot of material above it, and then we got a 6-inch floor slab. So that's also 2.5 feet. And just to keep it simple, we're going to call that all about 120 pounds per cubic foot too. Again, we could divide it up into, say, 145 for the concrete and 120 for the soil, but there's no point in belaboring. Plus, these are such similar numbers that for all practical purposes, this whole thing is going to zero out anyway. I mean, it's going to make, if we really went through and diced it into little tiny pieces, it'd be a very, very slight reduction because there's a little more concrete here than there is weight of soil out there, but it's not enough to worry about. So we're just going to say all that goes to 0, which is a common simplifying assumption. Of course, if this whole thing were 10, 12, 20 feet in the ground, then the surcharge would be more, and the weight of the foundation would be a lot more. So maybe those numbers would matter a little bit more. All right, but anyway, you add all those numbers together, divide by our factor of safety of 3, we get about 2,052 pounds per square foot net allowable. For the foundation loads that we were given, 75 kips and 50 kips, add those two together, divided by, say, 2,000 pounds per square foot bearing capacity. That gives us that we need 62.5 square feet. Take the square root of that since it's a square footing, and it says we need 7.9 foot wide foundation, okay? Now, turns out that the number that we originally assumed, 7.9 feet, here is B, turns out to be what we had. But if we had assumed 3 feet, that's quite a bit different from 3, so we'd have to go back and run it again until we got something fairly close. Now, had we assumed 8 feet and we got 7.9, then that would be fine, okay? All right, so I got some questions. Let's catch up here. Gary says, does C always equal 1/2 QU? Yeah, C always equals 1/2 QU when the shear strength is given to you in terms of unconfined strength. Now, if you have shear strength given to you in terms of a triaxial test result where you have a C and phi, then no, that's not right. But it's always 1/2 QU when shear strength is given by virtue of a unconfined strength. All right, Brian, where did the 0.85 come? The 0.85, let's show everybody where that is. The 0.85 is out here. That is the bearing shape factor for n sub gamma. Yeah, n sub gamma. And that came off the chart, Brian. We go back a couple of pages and you'll see that we had a chart for shape factors for n sub gamma and n sub c, okay? Let's see, where did the 62.4, we assumed that. You can pick whatever unit weight of water you like. 62.4 is unit weight of water because they're correcting from saturated unit weight to submerged unit weight, okay? And it does vary a little bit, but that's close enough. Where did the 2000 come from? 2000 is, we said, well, 2052. We could have divided by exactly 2052, but you know, you're using a factor of safety of 3, so the typical thing would be to kind of round off to the nearest value. But no, if you want to, Amanda, if you want to divide by 2052, you're going to get almost exactly the same answer. So, yeah, excuse me for, being the geotechnical engineer. We tend to kind of round things off because, let's face it, with a factor of safety of 3, it's just not going to make that much difference, right? Okay, Gary, how could you assume this footing is square? Correction factors will be affected. Oh, we didn't assume that. Okay, let's go back. We didn't assume that at all. Or did we? Yeah, no, we didn't. Interior square footing, okay, that was given to us. Okay, yeah, you can't assume that. Now, for a column, it would be a common kind of assumption, but not always. I mean, depending upon loading directions and things like that, you could have a rectangular column footing, or you could have a circular one, for heaven forbid. But yeah, good question there. All right, let's see, got a couple more questions. Oh, you're right. Yeah, I did say square. All right, let's see. How about the 2.5? Where did that come from? The 2.5 is the depth of material. We talked about that. You got 1 foot for the height of the footing, 1 foot of soil above the footing, and 6 inches, okay? All right, and last question here for a minute. How often does Q, N sub Q, gamma, DF cancel each other out? You know, usually they're close. And again, if we, if the unit weight of the soil were, say, 105 pounds per cubic foot, and unit weight of the concrete, especially if it were a big, wide pier footing with maybe a real thick pier on top there, lots of concrete, not so much there. But, for this kind of situation, a lot of cases, it's hardly worth considering, especially when you take into account the factor of safety of 3. Now, again, for your purposes on the exam, work it out in as much detail as seems practical. I doubt that it's going to be a minutia difference. They shouldn't give you the wrong answer if you assume 145 versus 150 for the concrete, let's say. But, in a lot of cases, that's just not a big factor. It's very common to assume they kind of cancel each other out unless you got a footing real deep in the soil or you got a really big footing. But, the answer for the exam is do it to a reasonable degree of accuracy to make sure that you're getting a good answer. All right. Let's see. Couldn't follow the third part of the equation. Could you please repeat it? Well, let's see. I'm not sure the third part of the equation. Let's just assume that we're talking about this is the first part. That's the shear strength of the bearing capacity from the friction in the soil. This is the bearing capacity from the cohesion in the soil. So I think you're talking probably about this part. And again, this is just simply 2.5 feet, which is the depth of the surcharge, okay? This third portion of the bearing capacity is the depth of the surcharge material. That's the soil and anything above the bearing level. So that's 2.5 feet. The unit weight of that material, and again, that's 120 pounds per cubic foot. This zone's 120 pounds per cubic foot. And the floor slab will be ever so slightly higher. Maybe it'd be 145, but you only got 6 inches of it, so kind of splitting hairs if you add another component to calculate that. But you could. And then this is the bearing capacity factor, and that's N sub Q for surcharge. Again, surcharge is anything that is adjacent to the foundation that's creating confinement that prevents this failure surface from breaking the surface and going up. Okay, so that's surcharge confinement. And then this last part, that's really not the bearing capacity. That is the correction for the net bearing capacity, and that's simply the weight of the foundation itself and any soil sitting on top of it. Okay, hope that answers your question. On the test, since this is an allowable question, would you then not end up canceling out the surcharge loads? No, not at all. Surcharge is to your benefit. Um, Oh, I'm sorry. Yeah, exactly. We've done that. We've said, okay, well, you're right. The net correction, based on the weight of the footing and the soil sitting on top of the footing, is very, very similar to the surcharge pressure down here. I mean, they're very, very different. So the dimensions are exactly the same. From the top of the footing to the bearing surface is exactly the same. The only difference is just the unit weight of the materials, which is why I showed us is just canceling out and going to zero. So yeah, that's exactly the point. Good question. All right, let's see, Jeremy. Need to check footing size prior to selecting Q.A. as your answer iteration based on B. Yeah. You have to. You have to start off with a B of some kind because it's in the equation, right? Here's B right there, 7.9 feet. So you gotta pick something. So, maybe just arbitrarily assume everything's 3,000 pounds per square foot, kind of based on the shear strength of the soil, let's say. And that's one thing you could do. You say, okay, the shear strength of the soil is 2, so I'm just going to assume the bearing capacity is a little higher than that. So let's just, say it's 50, 1.5 times that, or just use that value. That'd get you in the ballpark. And roughly decide how big that footing would be then, and then calculate your true bearing capacity, and then correct it if you're way off. Okay. All right. Q is given to be 1,800. That's Q sub U. That's the unconfined strength. Why did we use 2.5 times 120 instead? All right. It's two different things. This is Q sub U, which is a test result. Q sub U is the symbol used for unconfined strength. You're confusing that with the surcharge. Unfortunately, they are very similar. Q is the surcharge stress, but Q sub U is unconfined. Okay, sorry about that. That's just convention in geotechnical engineering. They must give you B. You can input B dimensions to the equation to get any answer they could give you. They don't have to give you B. I mean, they very likely would. But they don't have to. They could certainly ask you to calculate it and just see what you come up with. It's hard to say how they would phrase it, but what you generally find, assuming you assume something reasonable. Let's face it, most soils have bearing capacity somewhere in the range of about 2,000 to 5,000 pounds per square foot, so you're not going to be way off. Okay, let's say give you something with a really low shear strength or a really high shear strength. I mean, odds are you're going to be somewhere in that range, so it's not going to be a huge factor for you. All right, let's see, Michelle. I'm getting N sub C 5.7 using Terzaghi table. Okay, fine. Yeah, good. That's no problem. Again, the answers they give you have to compensate for little differences in one table versus another. Yeah, that's perfect. No problem. Could you input a B dimension to get any of the 5 multiple choice answers? Again, I think what you're going to find is the answers they give you are going to be far enough apart that so long as you correct your answer, if you assume something way off, it's just not going to be a problem. I think you're worried about that too much. So just assume something, either use what they tell you, if they tell you that, or assume something reasonable. And I think you're going to find that at worst, maybe you have to run through the equation twice, but big deal. All you got to do is change that one number out and everything else stays the same. All right, let's see here. Okay, I think we're all caught up. Good questions. Let's keep on going. We don't get too far behind here. All right, so let's assume now that we have a soil that doesn't have cohesion. Instead, we have a friction angle, and let's see what happens when we use that kind of a soil. So we have basically the same kind of equations, only now instead of an unconfined strength of 1.8 KSF, now we have no cohesion whatsoever, and all we have is a friction angle of 30 degrees, okay? So this is going to be real simple. So we're just going to do the same kind of thing. Everything else stays the same. The submerged unit weight for the friction surface down below the bearing surfaces, still got to use that. We're going to still assume that 7.9 feet. The bearing capacity factor N sub gamma for a friction angle equal to 30 degrees, though, by my read in the charts is now 17, okay? So you pull the charts up and look at it and just make sure you find something similar. It's still a square footing, so the shape factor is still 0.85. And then we're going to just go ahead and calculate the effect of the surcharge here. 120 is the unit weight of the soil, 2.5 is the depth of the surcharge over here, and the N sub Q bearing capacity factor is 20, okay? So we end up with 9,288 pounds per square foot. Now notice we don't have an N sub C factor at all, because since C is equal to 0, how do we know C is equal to 0? Well, we're not given any cohesion, and the only reference to shear strength is phi equal to 30, so the assumption is that the cohesion is 0. Okay, so there's no cohesion factor in here at all, doesn't show up in our equation, so our ultimate bearing capacity is 9,288. Now, if we want net bearing capacity, we subtract out the weight of the foundation, just like we did before, and we get this value. And now if we want allowable net, then we divide by a factor of safety of, say, 3, and we get about 2996, which, again, we're just going to say, let's call it 3,000 pounds per square foot. If you want, for the purpose of the exam, you want to use 2996, go ahead. It really shouldn't make any difference, okay? All right. So that's it. And again, we would calculate that out, see what size footing we got, just make sure that 7.9 is still in the ballpark. This is a little higher bearing capacity than we had before, so it's going to be slightly different from that, but we're not going to go back. You guys should have a handle on how to do these calculations, so we're not going to repeat that. All right, let's see. Matthew's got a question. Using the charts, N sub C at 30 degrees is a value. Yeah, it is, absolutely. At 30 degrees, N sub C is indeed a value, but remember the equation. It's C times N sub C, and C is equal to 0. This is not the same problem, but on the problem we were given where the only reference to shear strength is phi equal to 30 degrees, there's no C. So since C is equal to 0, then you don't have anything, okay? Why no cohesion? Because that's what they tell us. Yeah, all right, good. All right, and we're going to move past bearing capacity, and we're going to start talking about lateral earth pressures. Lateral earth pressure is simply the stress that is generated due to the characteristics of the soil, the loading conditions of the soil, and the depth of the soil, at whatever point we're looking at, okay? And so if we know our vertical stress, sigma V, which is just equal to the depth in the ground times the unit weight of the soil, so if we know our sigma V, then the lateral earth pressure, sigma H, is simply sigma V times some lateral earth pressure coefficient that we're going to use K. We use K for a lot of things, so just be careful that you realize what K means in a particular application. Now, the lateral earth pressures come in 3 different conditions. You have active earth pressure, which is the lowest value you can get, at-rest earth pressure, which is kind of an intermediate value, which is the condition that exists at all times when you're not causing the soil to change stress state. We're going to talk about that more in a minute, but at rest is kind of the condition that's in the ground all around now until we dig a hole, we start applying load, okay? So without some kind of a transitory load state, at rest is what you would normally have in most situations. And then passive earth pressure is really a capacity, because passive earth pressure only applies when you push on the soil. And we're going to talk about this more, but just remember there are 3 different coefficients because there are 3 different stress states. All right, so active earth pressure is a condition that we would have if we had a ground surface. Let's say this is a ground surface, and we came out at some point and we dug a big hole. Okay, so we have a vertical face, and we've just simply removed all the soil that used to be in this area and used to be pushing back on that wedge of soil, okay? So now that wedge of soil is being loaded by its own mass, okay? And so it's going to mobilize shear strength along all these planes in this area back here. And so it's going to be mobilizing shear strength along all these planes up from the horizontal, right? Well, the highest shear condition, the highest shear stress is going to develop along a plane that's defined by this value theta, which is 45 plus phi over 2. So it's a little steeper than 45 degrees. So this is a pretty steep angle, okay? And because this is a pretty steep angle, then that means this wedge of soil that is encompassed by that angle is a fairly small wedge of soil. And so active earth pressure is really the minimum pressure that you can get. And why is it the minimum pressure? Well, because the soil is trying to hold itself up. It's mobilized the shear strength all along here, and it's trying to hold itself up. Now, if it actually fell into the excavation, well, that wouldn't be a lateral earth pressure problem anymore. That'd be a slope failure problem, and then it would just be a sliding wedge type situation for the sake of our discussion here. But this is a situation where we come in and we stick a wall in there, and the question is, what kind of load does this soil that's backfill or just the wedge of soil that we stuck the wall against, what kind of load does that impose on the wall? Well, it imposes the load on the wall that is the leftovers from what this shear strength along this failure plane, along this mobilization plane, can't resist. So anything beyond that is what the wall has to resist, okay? And that can be estimated. The active earth pressure coefficient can be estimated for a friction-only soil as the tangent squared of 45 minus phi over 2, okay? Now, be careful. This is the minimum value. It's tangent of 45 minus phi over 2 for the coefficient. The angle that it makes relative to the horizontal is 45 plus phi over 2, okay? Tangent squared, 45 minus phi over 2 is the coefficient. Now, passive is exactly the inverse. You don't have passive resistance at all unless you push on the wall. You can never have a wall standing there that is generating passive earth pressure on its own unless it's resisting something, okay? Because passive resistance is what happens when you push on the wall and the soil wedge mobilizes its shear strength in exactly the reverse orientation. So instead of 45 plus phi over 2, which is a real steep angle, this is 45 minus phi over 2, which is a real flat angle. It's less than 1-to-1, less than 45 degrees. And numerically and physically, the active and passive are the absolute inverse of each other. Numerically, it's 1 over Ka or tangent squared of 45 plus phi over 2 for the passive earth pressure coefficient, okay? Big wedge of soil, large values, but you only get as much as you need to resist the forces that you apply. Now, if you load it too much, then the wedge just slides up out of the ground. You have a passive earth pressure failure. But passive earth pressure is really not a load. Passive earth pressure is really a resistance, kind of like sideways bearing capacity, if you will. Okay. All right, and then at-rest earth pressure is the load that you have on the wall when nothing can be mobilized. In other words, the shear strength isn't mobilized because the wall doesn't move enough to allow it to be mobilized, and you're certainly not pushing on the wall. So at-rest earth pressure is the pressure you have when the shear strength is not mobilized along those failure planes. Okay. All right, got a couple questions here. Let's catch up. Okay, I think we already answered that one. Yeah. For N sub C on that previous problem, yeah, if you had N sub C, phi equal 30, you do have an N sub C value, but you got no cohesion, so it doesn't do any good. Let's see, Matthew, why? So why no cohesion? Because they didn't give us any cohesion. That's given in the problem, okay? The friction angle is equal to 0. Or excuse me, the friction angle is 30 degrees, and they don't give us cohesion. All right, Todd says, does Kp 1 over it, if it is not a frictionless soil? Not a frictionless soil. Yeah, well, for the purposes of this discussion here, we're only talking about friction soil because the only value you got is phi, okay? So it has to be a friction soil to use these values at all, okay? If it's a cohesive soil, we're going to talk about that in a minute, Todd, so just hang on. But, yeah, this is only friction soil. Yeah. All right, talked about that. Now, here's what these look like. The active and the passive earth pressure are failure conditions. You're right at the failure condition where you've mobilized all the shear strength. So they're actually going to be points on the failure envelope. And so they're defined by those relationships. At-rest earth pressure is not a failure condition. It's just a stress state, and it is something that just exists in the ground. There's no reason for it to be at a failure condition. So it doesn't touch the failure envelope. So we estimate the at-rest earth pressure based on Poisson's ratio, or it can be estimated based on the friction angle. It's a very common kind of relationship to use that we're just going to assume for the purpose of our discussion today is valid. But there's a great deal of research on just how you estimate that, and certainly for cohesive soils, at-rest earth pressure coefficients are based on a lot of things like pre-consolidation pressure, plasticity, all those kinds of things. But for a friction-only soil, 1 minus sine phi is probably the most common way of estimating it. Okay, but again, it's not a failure condition, so it's not a point on the failure envelope. Okay, a couple different theories, Rankine and Coulomb, both researchers. Coulomb developed his equations first. They're very similar looking. This is Coulomb's theory. Coulomb takes into account this interface friction between the back of the wall and the soil, whereas Rankine typically does not. But they're very similar. If you take that coefficient out, they're very, very similar. Coulomb was actually a researcher, a French researcher, and same guy that developed Coulomb's law in current movement around a circuit, if you might recall from school. So smart guy, researcher in the French military about the same time as the American Revolution, so back in the 1700s. Then Rankine came along later and developed something very similar. And so it doesn't really matter which set of equations you use. Most of the common ones you see are based on Rankine analysis, and you'll see Rankine analysis later on that has a provision for cohesion. Coulomb never really considered that, but again, if you take the delta value out for the interface friction along the back of the wall, they're pretty much the same equations anyway, so it's not that big of a deal. All right, and again, use whichever one you like, unless on the purpose of the exam they tell you specifically which one to use. All right, let's see. I think we're all caught up. All right, so let's go through and just see how this would be used for an active lateral earth pressure condition. What does that mean? Active lateral earth pressure condition would be like if we had a cantilevered retaining wall, and a cantilevered retaining wall is really not very rigid up here, so it could deflect ever so slightly and just deflect enough that we could mobilize that shear plane back behind it, right? Now, if this were a rigidly supported wall with shear walls, let's say a basement wall where the top of the wall is constrained by floors and it's got intersecting shear walls, and there's just no way for that wall to deflect, then maybe you want to design that thing for at-rest conditions. But a cantilevered retaining wall and pile walls and things like that are usually designed for active earth pressure conditions, so long as that wall can tilt outward a little bit, rotate to accommodate that. All right, so what is the pressure at the base of this wall, the maximum lateral earth pressure? Well, it's going to be the vertical stress, which is the depth of soil times unit weight of soil times lateral earth pressure coefficient. For the active state, we've said K sub A is tangent squared of 45 minus phi over 2. Therefore, the pressure down at the base of this wall, the maximum pressure, is going to be the depth of the soil times unit weight of the soil times tangent squared of 45 minus phi over 2. Now, what is the load, the full load imposed on this wall by all of that backfill soil? This wedge-shaped, linearly increasing stress diagram is a triangle, okay? So the load, big P sub A, which is the entire force per foot, unit foot into the page, that is acting on that wall, the full height of that wall, is the area of that triangle. So it's 1/2 the base times the height, right? Just the area of that triangle. So gamma K sub A d squared over 2 is the normal way of calculating the full load applied to that wall. Okay? All right, we've got a question here. Let's see, Ryan. So use K sub P and K sub A for flexible retaining walls and K naught for rigid. Yeah, I think that's, well, K sub A, active certainly for flexible walls. K sub P is only applied when you're pushing on the wall. Again, and sometimes that just means, as you'll see later on, that the backfill on one side is pushing on the opposite side. So the active pressure is the load, and the passive resistance is the resistance. And K naught, yeah, if the wall is inflexible and can't move. That's exactly right. All right, so we have this wall here. The unit weight of the soil is 122. The friction angle is 24 degrees. It's 12 feet. Let's do some calculations here. So we calculate our lateral earth pressure coefficient of 42, of 0.42 rather, and then the pressure at the base of the wall, 12 feet times 122 times our 0.42 means we have 615 pounds per square foot. And then our total load then, if this is 615 and the height is 12, it's just the area of that triangle, 1/2 the base times the height. So the entire load is 3,689 pounds force, big P sub A, okay? Real straightforward, just plug and chug kind of a thing. All right, now let's do our passive earth pressure. Let's just say we're pushing on the wall, and what is the maximum passive resistance we can get? Got a unit weight of 122, a friction angle of 24 degrees, passive earth pressure coefficient, tangent squared of 45 plus phi over 2, 2.37, big number, right, compared to what, 0.42 for active? And so our maximum pressure down at the base of the wall is 12 feet times 122 times 2.37, so 3,470 pounds per square foot compared to, what was it, 680 for the active maximum pressure down there. And then big piece of A, the full force acting due to that stress triangle there is 1/2 the base times the height, or 20,000 pounds of force, 20,818. Yeah, big force, big capacity. Based on that loading condition. All right, got some questions here. What is PA versus, little p sub A is the maximum pressure at the base of the wall, or the pressure at some point. Little p is pressure, big P is force, okay? Not seeing questions here. I'm not sure what you mean by that. These are the kinds of questions they might ask you. They might just ask you, calculate the pressure at the base of the wall, calculate the maximum active loading acting on this 12-foot high wall. So you can make up your questions if this is what you're asking, Jeremy. Yeah, there's lots of different questions they can get out of the illustrations that we're going through here. And you're going to see here in a few minutes a much more involved kind of problem that we can use to apply here. Okay? All right. All right, here's good, some more information here. Now, this is what happens when we apply cohesion to these equations, too. Here's the base cohesionless calculation that we've been talking about so far. So this is for a phi-only soil. But when we add cohesion to that, then it affects the shear strength of the soil behind the wall, right? Therefore, it's going to affect our pressure coefficients, or our pressure. But remember that what happens is the cohesion adds to the shear strength of the soil. So this is the lateral earth pressure coefficient, or the lateral earth pressure at the base of the wall, and based purely on friction. And if we have cohesion that's added into that, that's actually going to reduce the loading on the wall. So for the purposes of active earth pressure, it's going to reduce that pressure, since active earth pressure is a load. So it's minus 2 times cohesion times a tangent of 45 minus phi over 2. So that's how you would take that into account if you had cohesion in the soil behind the wall. Okay, and then big P sub A, which is the total force acting on that, is just going to be that same equation, the area of the triangle, minus 2 times C times the height, obviously, because we have cohesion all along that entire shear plane, times 45 minus phi over 2. And again, this is for the active condition. For the passive condition, it's all the exact same equations, except all the negatives turn into positives, okay? So exact same relationships. You can find it in your references, but just to show you that it's always the inverse, passive versus active. All right, now, so let's do an example problem here. We have, let's see, we got a question, Matthew. Under what circumstances would you use passive instead of active pressure? Passive is always a resistance, okay? Passive never develops on its own. Now, you never have a wall that's being loaded by passive earth pressure. You might have a wall that's being loaded by active earth pressure because that's the wall's flexible and you develop that, or maybe the wall's not flexible and so it's being loaded by at-rest earth pressure. But passive comes into play because the soil on the opposing side, here is the loaded side of the wall here in this cantilevered retaining wall. This is the backfill zones up here, so all this is load, but it's pushing the wall laterally. And so our resistance is over here on this side. So this ends up being passive resistance over here. So that's when you would use it, when you have something that is pushing on the soil. It could be a retaining wall like this. It could be a dead man anchor. Those are situations in which you would use passive resistance. All right, so let's crunch through this here. We got a cantilever retaining wall. It's 10 feet tall. The footing's a foot thick. The wall itself is a foot thick. We got a 3-foot wide heel area. We got a 4-foot wide toe area. So we have soil with a unit weight of 100 pounds per cubic foot. Friction angle is 30 degrees. There's no cohesion. So let's crunch some numbers here. Active earth pressure coefficient for 30 degrees is tangent squared of 45 minus phi over 2. Or we can use another equation, which is 1 minus sine phi over 1 plus sine phi for active earth pressure coefficient. For passive, it would be the inverse of that. Okay? So that gives us 0.33. The passive earth pressure coefficient is tangent squared of 45 plus phi over 2. And so for 30 degrees, that gives us a passive earth pressure coefficient of 3. Okay. Maximum active earth pressure at the base of the wall back here is going to be the unit weight of the soil times the lateral earth pressure coefficient, 0.33, times the height of the wall, which sets 11 feet, 10 plus 1. So that gives us 363 pounds per square foot maximum pressure down here at the base of the footing. The resultant force, which is the entire force due to that triangular stress diagram there, is going to be the area of that triangle, 1/2 the base times the height. So 1/2, 363 times 11 feet, so 1,997 pounds per foot into the page, right? All right, now what's the moment? This trying to, since this is a triangular-shaped stress distribution, it's going to act a third of the way up from the base. And if this thing's going to flip over, it's going to rotate about the toe here. So this, we're going to call that point A, and we're going to take moments about that point. So the force acts a third of the way up from the base. And so that's 11 divided by 3. So that's our moment arm is 3.67. So the moment then is 3.67 times our passive earth vector or force, which was 1,997. So we get 7,329 foot-pounds per foot into the page. All right, let's see here. Now, this looks a little complicated, but it's not. We'll just go through it real quick. All we're doing here is resolving forces because we're getting ready to take moments around the toe to see whether or not this thing has an overturning problem. Okay, so we're going to take moments around the toe or point A. And so each of these is just an area of the structure itself. The wall itself is 10 feet wide by a foot thick, so that's 10 square feet. And we're going to call the concrete 150 pounds per cubic foot. And the V just means it's a vertical force acting downward, right? The weight of this concrete is a vertical force acting downward. The footing itself is 8 feet long, and it's a foot thick. So again, that's 8 times 150, also a vertical force acting downward. The backfill over here is 10 feet by 3 feet. That's 30. The unit weight of the material was given to us is 100. That's a vertical acting downward load. And then we have passive resistance. Where we have passive resistance? Well, over here in this little soil area, it's a foot deep from the top of the footing down to the bottom of the footing. So we got this minuscule little footing area. And so our passive earth pressure is going to be 1/2, 3 feet, or excuse me, 3 is the passive earth pressure coefficient times 100 pounds per cubic foot, so weight of the soil, and then depth is 1 foot. So we got a little dinky 150 pounds per linear foot of pressure, passive earth pressure over on this toe. It's a little bitty here, but in some cases your footing might be a lot deeper, so it would be a lot bigger, so we don't want to forget about it. So that's 150 pounds of linear foot pressure, and that's horizontal, okay? All right, so if we add all of our vertical loads up, that's 5,700. We ignore the 150 because that's a horizontal force. All right, and then our moment arms for each of the areas here, resulting moments, keeping our signs straight so we know which way they're rotating. And so the sum of the moments is 31,100. Okay. So then if we take our overturning moments, resisting, which are all the forces that are rotating counterclockwise, those are all the resisting forces, and divide that by driving. And driving are all the forces that are trying to push the wall over clockwise, which really is just our active earth pressure, right? And we divide those two, we get a factor of safety of 4.2 for overturning. So clearly this is not going to fall over. All right, a couple questions here. Matthew, on page 35 under resultant force y is h squared. Because we're taking the area of that triangle. We want the h is squared because we are taking the area of the triangle. The area of the triangle would be 1/2 the base. The base is k sub a sub gamma times h, right? So there's 1h. And then the area of the triangle would be 1/2 the base times the height. Well, the height is also h, so that's why h is squared, okay? Just the area of the triangle. Good question. Can you take a moment on another point? Take the moment of another point. Okay. Sure. Yeah. I mean, why did we take the moments about this point? Well, because we want to see whether or not we got a problem relative to overturning. So since we have the load applied here, where else would it pivot? Okay, you can take moments about any place you want. You can take them about the base of the wall. You can take moments about the heel, but that's not really telling you anything. The reason we took it about point A was because we were trying to see what the factor of safety was relative to overturning, and clearly in this scenario, it's going to rotate about the toe there. Okay, so that's why we did it there. Good question. All right, sliding resistance. So the sliding resistance is going to be the base friction plus the passive pressure at the toe. Okay, well the base friction is just simply going to be the weight, which we calculated a few minutes ago. Here's the vertical weight, 5,700 pounds. Okay, and so the base friction is going to be friction at the base, 5,700 pounds, times a tangent of 2/3 of phi. Now, why 2/3 of phi? Well, phi is the shear interface friction from soil to soil particles, okay? When we're going between soil and a dissimilar material, we have to apply some kind of reduction. And there's lots of charts you can get. I'll show you one a little bit later that shows you what those reduction values are. But for rough concrete on soil, something like 2/3 of the friction angle is typical. All right, so that means our base sliding friction is 2,075 pounds. All right, so we add that to our 150 pounds of passive resistance, and we divide that by the horizontal force that's pushing this whole thing, which is 1,997, which was the active horizontal force, right? And we got a sliding resistance factor of safety 1.1, which isn't very high. So really, if we were doing the design, we'd dig this footing a little deeper. We'd put a keyway down in there, or a stem, or something like that, because we want a little higher factor of safety than that. Okay, all right, question here. Ryan, how did you get to 7,329 again? All right, let's back up and get that. 7,329 is simply our, that is our driving moment, right? Our driving force is 1,997. That's our horizontal force due to the active earth pressure. Our moment arm is 3.67 feet. That's just the distance from where the force is applied down to this plane where we're taking moments, and that gives us the 7,329, okay? So that's just the overturning moment. That's the driving moment, if you will, and that's why we stick it there in the equation, okay? Real simple. All right, let's see. Did we already cover this one? Nope, we didn't. All right, so with sliding resistance, factor of safety is 1.1, not too good. All right, now the next thing we're going to do is going to check eccentricity. Why we want to check this? Well, because this is not a symmetrically loaded foundation, okay? We got soil back here and nothing but air on this side. So we know that our bearing capacity, our bearing pressure is going to be higher on one side versus the other because we got all the soil back here and nothing over here. So the question is, of all the loads that are applied, both the overturning moments and the vertical loads, what does that do to our bearing pressure? We want to make sure we don't end up with too heavy of a load out on the toe and cause some kind of a local failure, or we want to make sure we don't have tension acting on the heel or something like that. All right, so we're going to just check the eccentricity, and we check the eccentricity by summing all the moments, and then we divide that by the vertical forces. And why do we divide it by the vertical forces? Because we're trying to find the eccentricity relative to the vertical axis, okay, out from point A, okay? So if we do that, we got the sum of the moments is 23,771, and the sum of the vertical forces again was 5,700. We just used that. It says our eccentricity is 4.2 feet from A, which is more than halfway across the footing because the footing is 8 feet wide. 3 plus 1 plus 4 is 8. So we're 4.2, which means that our eccentricity is back here on the heel side, okay? So a little bit beyond, which means what? This is going to be a heel-loaded structure. So the pressure is going to be a little higher back here on the heel side. If we don't know exactly what that number is, then we can just calculate our base pressure based on the classic equation Q over A plus or minus MC over I, calculate all that out, and you'll see that it's 712.5 plus or minus 106.8 pressure, all right, which means we have 819.3 pounds per square foot on the heel. Well, we expect it to be a little higher, and only 605.7 out here on the toe, okay? Now, the only thing tricky about this whole thing is which direction do you take as your height for the purposes of calculating your moment of inertia? Well, remember, since we are looking at the pressure to be higher or lower on the toe and on the heel, that means the extreme fiber stress, if you will, are this end and this end. So H is 8 feet from one point to the other over which we're going to dissipate these stresses, okay? So just be careful. Some people think that H is 1 foot because they're used to thinking about this thing in the beam, but really our H is horizontal in this particular case. Okay, let's see. Gary got a question here. Why not use the coefficient of friction between the base and the soil? Well, we are using the coefficient of friction between the base and the soil, but they didn't give us that value. They gave the only information we're given is phi. So had they said, well, it turns out the coefficient of friction between the base and the soil was 24 degrees, we would have used that value. But since all we had was phi, we just had to pull some kind of reduction value off the chart. And again, there's lots of references for those, but that's where we got it. Hopefully that answers the question. All right, Donald, how would a keyway add to the sliding resistance? Well, it would certainly increase passive resistance. The shear strength of the soil, let's presume, is all the same. So in that sense, it wouldn't increase sliding resistance relative to the friction along the bottom. But if you have a keyway in there, then you're going to have more passive resistance, right? All right, for sliding, isn't it horizontal force times coefficient friction divided by vertical forces? No, I don't think so. Let's go back and see what you're saying, Gary. Let's see. For sliding, where's sliding? Well, I mean, our sliding factor of safety is a function of resisting divided by driving forces, and so the horizontal force is the driving. That's created by the active. Okay. But the vertical force is not a driving force. The vertical force, which was our 5,700, okay, that's pushing down the foundation, which is activating our friction. Okay, so no, you got to do it. Maybe I'm missing your question, but hopefully that. Oh, maybe the opposite. Well, I think I explained it. So hopefully that answers your question. If it doesn't, try me again. But I think it's right the way it is. All right, let's see. Michelle, why is the equation 2/3 of phi? I see an equation of just W times tan phi. Equation of W times tan phi. Not, well, this is W times tan of 2/3 phi is the equation I'm showing you here. And the equation is 2/3 of phi because you have to take some kind of reduction because you don't have just phi. You don't have soil acting on soil. You have concrete acting on soil. So that's why it's not just tan phi. Okay, good question, but we're going to see some more of that here in a few minutes. So just hang on. You'll see more evidence of why that's the case. All right, this is exactly the same thing. It's just worked through with a slight different set of equations. Instead of Q over A plus or minus MC over I, you can get Q over B times 1 plus or minus 6E over B. Depending on what school you went, you might be more familiar with that one. All right, let's do a anchored bulkhead. This is a cool kind of problem, and you're guaranteed almost. It's kind of like I was talking about the Barrel problem on Tuesday. Cantilevered retaining wall and probably some kind of anchored bulkhead, especially the cantilevered retaining wall. Almost guaranteed to see one of those things on the exam. Anchored bulkhead, a simple one like this is pretty common too, so you need to be familiar with how to do this. Same kind of sort of thing we've already done here, so let's just go through it real quick. Earth pressure coefficients for active condition, tangent squared 45 minus phi over 2, passive, tangent squared 45 plus phi over 2. Here are the values that we get, 2.27, 3.7, okay? Now, we don't know the force in the anchor. Why don't we know that? Well, they haven't given us that, okay? So we know we're going to want to take moments about the anchor to check to see whether the toe kicks out or not. And one nice thing about taking moments about the anchor location itself is that we don't have to know the load on the anchor. So since we don't know that, it's a good place to do it. It also happens to be where the water surface is. All this out here is soil. This is the dredge line, meaning everything above, that's water up to the water symbol. And all this over here is soil too. Now something else you have to realize for this purposes of this problem, we're assuming that if there's water over here, there's water over here because they haven't said anything about this wall being impermeable. If they said it was impermeable, then there wouldn't be any water over here maybe. But for all practical purposes in this kind of situation, if there's water on this side, then the assumption is the water is equal to or maybe even slightly higher if they show it that way on the soil side. Okay, so the active pressure at the anchor is 110 pounds per cubic foot. 0.27 is our earth pressure coefficient. 8 is how deep in the ground we are. So we have 237.6 pounds per square foot at the anchor and at the groundwater surface, okay? At the base of the bulkhead, which is down here, another 26 feet in the ground, there's the 26 feet. We have that 237.6 feet, plus we have 110 pounds per cubic foot, which is the unit weight of the soil, minus 62.4 because now we're submerged unit weight, right? Active earth pressure coefficient 0.27. So down here, the combination of those two is 571.8 pounds per square foot. That's the maximum pressure down here at the base of the wall. Okay, so here we show the pressures that or the stresses that we've now calculated. And then over on the passive side, okay, I say it's passive side because active side is over here, and so it's going to try to push the wall over. So we're assuming that we're going to generate some amount of passive pressure over on that side. We also think that that's the mode that it's going to fail in because since we have an anchored wall up here, it's not going to rotate very much outward. And so the active earth pressure over on this side is simply going to try to shove the bottom of the wall out, which means we're going to generate passive pressure over on this side. Okay, so just using our passive earth pressure coefficient, 3.7, we're definitely submerging it way over there on the dredge side. We get 2,465.7 pounds per square foot, and the entire force from the passive earth pressure, again, it's just the area of that triangle, 1/2 the base times the height, so 17,259.9 pounds per foot into the page, okay? All right, so if we show all of our forces here, the 950 for the triangular shape up at the top, the 4,344.6 for the triangular shape at the bottom, the 6177, which is the uniform load from here down to here due to that 237.6 pressure up here, it's just uniform. And I did it this way to make the moments easier to find because this would be a trapezoidal shape down here, so I'd have to spend some time determining what my center of gravity is and figuring out the moment arm. So just do two forces. You got one triangular, one uniform, and it makes it real simple. Okay, and then we got a triangular load over here. Okay, all right. All right, so now I can calculate the factor of safety for toe failure, which would be rotation about the anchor, which would just make the toe kick out. Okay, so again, the factor of safety is resisting forces divided by driving moments, and so the driving forces are going to be the 950.4 pounds, and its moment arm is 1/3 of 8. Now, we put a negative sign on that because relative to the tie back here, that's acting counterclockwise, okay? And it's acting counterclockwise, whereas the rest of the forces below the anchor are acting clockwise, okay? So that's a negative driving force because it's trying to help out the passive resistance over here on this side. And it's doing that by reducing the driving forces, and you'll see that's the way we apply it, okay? And then we have 6,177.6 times 26.2. That's the uniform load here. So it's just halfway up, 26 divided by 2. And then the triangular shape of 2/3 of 26 times the 4344. Again, driving forces. Resisting force is simply the passive resistance. It's also counter-clockwise, so it's keeping our sign straight there. And so if we do that, add them all up and divide the resisting moments by the driving moments, we've got a factor of safety of 2.4. So it's not going to fail by kicking out around the toe because we have plenty of embedment of our anchor. Okay. All right. And what was the force in the anchor? Well, there's a lot of different ways we could get that actually. We could take moments about the toe, but as it turns out, there's really not a huge error if we just sum the horizontal forces. It's the easiest way to do it, the quickest way to do it, and so that's usually the way you start is by just doing it that way. And for all practical purposes, that the fact that they're ever so slightly not collinear and doesn't usually create a big error. So that's a simple way and most common way of doing this. So we're just going to sum our horizontal forces, sum of the passive minus the sum of the active forces minus the passive resistance and divide that by 3, which means that since the passive resistance is divided by 3, it means the tension in the anchor has to be that much stronger by the factor of safety, okay? So if we do that, then we end up with 5,719.3 pounds per foot of wall into the page, okay? And if we say, well, let's just assume our anchors are 5 foot on center, then that means each anchor has to be 5 times that value, or 28,597. Now you can see a whole lot of different ways that they could come up with problems and questions that you could ask that we've just gone through in one system and analyzed probably a half dozen different kinds of equations and problems that they could ask you to address, okay? All right, so that's a tied back wall design as opposed to a cantilever design. All right, we need to move on here. If you have questions, send them in, and we'll get to them as quick as we can. We're going to talk about pile capacity, just conventional pile capacity. And we drive a pile in the ground. We're going to get resistance from 2 sources. We're going to get friction or side shear. Could be adhesion or cohesion along the side. So it's side shear. And then we're going to have end bearing, okay? And so we can have end bearing doesn't do much for uplift, but side shear certainly would resist uplift. But we're going to, for the initial time, we're going to talk about pile capacity in terms of downward axial loads, okay? All right, so the tip capacity then is going to be the area of the tip times cohesion of the soil down below the tip times the cohesion bearing capacity factor plus the confinement times the confinement bearing capacity factor. Okay? All right. All right, now for the cohesion bearing capacity, one of the things we discover is that as the footing width B, or the pile width B, is compared with the depth in the ground, Z, that after that ratio gets up around about 9, up around about 4, that ratio of Z over B gets up around about 4, that the bearing capacity factor pretty well flattens out at about 9. And since almost all piles are more than that ratio, for all practical purposes, when we're talking about cohesive soils, the bearing capacity factor in piles, N sub C for cohesion, is usually just assumed to be about 9. Now for cohesion-less soil, the bearing capacity factor N sub gamma, N sub Q, is going to be related to the friction angle, okay? So here's a friction angle here, phi, starting at 26 degrees going up to 40 degrees. And we have 2 columns, or 2 rows of values as a function of phi. We have these values, which is for driven or displacement piles. And that's any kind of pile that's installed where the soil never has an opportunity to relax into the void or into the annulus. So any kind of driven or pressure-injected type of pile is a displacement pile. And then this second row would be for something like a drilled pier, where at some point the soil is removed, the stress fields can mobilize, squeeze into the hole ever so slightly, and when the concrete or the grout or whatever is only installed at static head level, so you lose a little bit of the confinement of the continuity that you get from a displacement pile, okay? One thing that's confusing is, generally speaking, an auger cast pile is considered to be a displacement pile because the grout is injected at high pressures. So even though they're drilled by virtue of the auger, they are considered to be a displacement pile. Okay. Now, how about side shear along the sides of the pile? It's going to be the cohesion times some kind of a cohesion reduction factor times pi dl, which is just the surface area of the pile. And for friction, it's going to be lateral earth pressure coefficient K times the confining stress P times the tangent of delta, which is the interface between friction between the soil and the pile material, whether it's concrete, wood, or steel, whatever. And then again, pi dl is the area of the surface area of the pile. All right, adhesion to cohesion reduction ratio. Cohesion is the strength of soil on the same soil, so soil moving over soil. Adhesion is when the soil tries to grab something, and so it's slightly different values. And what you will generally find is the softer the soil is, the lower the shear strength of it is, the more cohesion can turn into adhesion. But the stiffer the soil is, the higher the shear strength is, the harder it is, it's less malleable, so the less of the cohesion can turn into adhesion. So if we have something that has a cohesion of about 500 pounds per square foot, something like about 90% of that, 0.9, can turn into adhesion. If we have something of about 2,000 pounds per square foot, then maybe only about 40% of it can make it into adhesion. Okay, so just remember, you have to take a reduction because cohesion is soil on soil, adhesion is soil on a dissimilar material. Lateral earth pressure coefficients, you have earth pressure coefficient when the pile is in compression, and you have a value when the pile is in tension, because when you're pulling on it in tension, there's a tendency for it to elongate and slightly narrow in terms of the stress field. In compression, foreshorten and slightly bulk at a microscopic level, let's say. And so there's a little bit, usually there's a little bit of reduction taken. You see these lateral earth pressure coefficients are a little lower in tension than they would be in compression, okay? And these are different earth pressure coefficients based on displacement, our jetted piles, so on and so forth, just based on research. There's lots of those charts out there you can use. Interface friction value delta based on the type of pile you're installing, steel, concrete, timber, 20 degrees, 3/4 of phi, just whatever looks like it's appropriate. All right, so let's do an example. 10-inch diameter concrete pile. Shear strength is given by QU is equal to 2,800. In this case, they're telling us phi is equal to 0. We know if QU is equal to 2,800, that's the unconfined strength, that cohesion in the absence of a friction angle is going to be 1/2 of that, or 1,400 PSF. Our moisture unit weighs 120 pounds per cubic foot. We have to assume that's the only value you're given. We have to assume that that's moist mean saturated, since we're below the water table, it looks like. All right, the diameter of the pile is 10 inches, so the end area is 5.54 square feet. And the surface area from the ground surface down to the tip for the 50 feet is 130.4 square feet. Just some numbers to get out of the way there. Okay, tip capacity then is going to be the area of the tip, 0.54 square feet, times 1,400, which is cohesion, times our cohesion bearing capacity factor, which again we said was 9 typically. So the tip capacity in this clay-y environment is 6,804 pounds of capacity. The side shear then is going to be 1,400 times our adhesion to cohesion reduction factor, and just based on the shear strength of the soil, 1,400, we picked that off the chart at about 0.6. About 60% of cohesion turns into adhesion. And then the 130.4 is the surface area of the pile, right? All right, so we end up at 109,536 pounds. Add those two values together, divide by 2,000, it shows us we have an ultimate capacity of about 58 tons for a factor of safety of 2, which is typical for pile design. We got a working load of about 29 tons. Okay. All right, here we got a question. Let's see, Brian. What is a jetted pile? Good question. Jetted pile is a pile that is installed by basically having a drill rod with a jet nozzle on the end of, on the tip of that, and the jetted pile is created by basically shearing the soil by a high pressure jet of grout that goes out. And so that makes a hole, makes an annulus. And so you just simply spin that into the ground and inject grout as the pile is the rod is removed and flushing grout out through it. So there's a bunch of different types of jetted piles. Some use different types of mandrels or other setups, but basically it's a pressure injected kind of pile. Now, another type of jetted pile that you see from time to time is one that's actually a fixed pile, but it's installed simply with water jets. Okay, so it kind of depends on what system they're using, but in some cases they simply, because sand is very readily removed with a jet, they simply put a jet on the tip of a fixed section pile and just simply jet that into the ground using that way too. So you got to be careful with how that's used, but it's a similar kind of effect, and the jetting is what makes the hole, and then you either set the mandrel pile or the precast pile section in there, or you backfill it with grout as you come out. A couple different ways that can be done. All right, pile capacity in sand. The one we did a few minutes ago was in clay, and The question here in sand is, we know our confinement increases with depth, and so the question is, does the benefit of the side shear increase infinitely with depth? In other words, if it's a 500-foot deep pile, is it 500 feet times the unit weight of the soil is the confining stress down there at the bottom of the pile? And the question is yes or no. I don't know if anybody knows the answer to that. If you do, type it in and let me see what you got. The answer, unfortunately, is no. There's a thing called the critical depth, and what happens, depending upon the density of the sand, once you get down to about 20 diameters for dense sand, you start to get a lot of arching effects, and so from below that level, you have uniform confinement. It doesn't certainly doesn't decrease, but it simply doesn't increase linearly anymore. You just have that same pressure for the rest of the length of the pile, which we'll see in just a second. Okay, excuse me there for a second. All right, let's crunch through one of these. Here we have a pile in sand. Let's see, the unit weight of the material is 120 pounds per cubic foot. Where is the? We still have the same properties here. How do we know the friction angle? Let's see. Okay, well, we'll get to that in a second, I guess. All right, so the confining pressure here at the top of the ground is P sub 0 is equal to, P sub 0 is equal to 0. There's no confinement at the top. Down here at 20 diameters, which for a dense sand, we're saying, is 16.6 feet. So we have 16.6 feet, which is the critical depth. 120 is the saturated unit weight minus 62.4 means that the maximum pressure we're going to have is 956.2 pounds per square foot. Now, at the base of the pile, we also have 956.2, so we still have many feet of confinement, but it's at that same pressure. It doesn't increase linearly with the depth. Okay. All right, here we go. So we have a friction angle equal to 30 degrees, and so our N sub Q is 21 based on the bearing capacity chart. Our K, confinement lateral earth pressure coefficient, is 1.5 based on the pile type we have. Our delta, based on the pile type we have, is 3/4 of phi, and so that means it's 3/4 of 30 degrees, so that's 23 degrees. So the tip capacity then is going to be the area of the tip, 0.54, times the confining stress, which is 956, times the bearing capacity factor, which we said was 21. So our tip capacity, or end capacity, is 10,841. Our side shear, or friction along the sides, then, is going to be earth pressure coefficient times the confining stress, tangent of delta, which is interface friction, times the surface area of the pile. And we're going to divide this up into two sections, because for this upper section A, down to 16.6 feet, it's linearly increasing with depth from 0 up here at the ground surface down to 956. So we're just going to take the average of that for this initial section. Okay, so it's 1.5, which is the K value. P is an average of 956 divided by 2. The friction then is a tangent of 23 degrees, and pi 0.83, 16.6. That's our area. Okay, so that gives us 13,174 for that portion. And then for the lower section down here, from 16.6 down to 50 feet, it's just 1.5 times a uniform 956. The rest of the equation is the same other than the length, which is 33.4. So that gives us 53,012 pounds. And if we add all that stuff together, gives us an ultimate capacity of 77,027 pounds divided by 2,000 is 38.5 tons ultimate. Factor of safety 2 means we got a working load of 19 tons. Okay. All right, we got a question here. Are slurry walls considered a type of pile? Well, that's a good question. Certainly the analysis technique would be similar in terms of the load resistance and how you could calculate the resistance to the vertical applied load, which is what we're doing here. Now, slurry walls, of course, are typically well, slurry walls can be used for a lot of different things. In some cases, they're put in and they're just a seepage barrier. But in some cases, they're put in and then one side is excavated. So those will be heavily loaded from a lateral load standpoint. okay? But in terms of the axial downward load resistance, they would be kind of similar, except that if you're going to excavate on one side, then you're going to lose all the adhesion and confinement of that. So you have to be careful of that. But that's a good question. They're kind of sort of could be, but it kind of depends on the loading application or the usage. All right, let's see here. Yeah, we're done with that. Okay, we're done with piles for a bit, and we're going to start talking about some other things. And first thing we'll do is talk about settlement calculations. We did this a little bit on Tuesday, just going through the E log P curve and so on and so forth. And here is the general general settlement calculation, one-dimensional consolidation theory based on Terzagh's research, which basically says, well, I want a settlement of a layer, which is the change in height of that layer, if that layer is of height h, then the total settlement of that layer is that height h times the change in void ratio due to my change in load divided by 1 plus the initial void ratio, okay? Now, if I don't have a E log P plot and all I have is the compression index, C sub C, then I can also use this equation, which is just based on calculating the change in the void ratio due to the slope of the E log P, which is the coefficient compression index C sub C. So let's do a problem here. We have this situation here. We've got a footing. It's a 10 by 10 footing with 150 tons on it. It's 2 feet from the ground surface up here down to the top of the footing, then another 2 feet down to the bottom of the footing where the water table is. We got 5 feet of saturated sand, and then we got 12 feet of clay, and then we have rock, okay? So there's a couple different things that are going to affect settlement here, but the clay primarily is the settlement target because clay consolidates in accordance with Terzagh's theory. Sand really doesn't. There's a different methodology that we're not going to have time to look at here today called Spertman's, and sand essentially is a elastic compression type of calculation with some simplifying assumptions. But we're going to look at compression of the clay layer. So the question is, what is the stress change, delta P at mid-height in the clay layer? Now, why mid-height in the clay layer? Well, we're going to be very clear about this. We're going to do this calculation to illustrate how the calculations are done. If you would normally calculate settlement of a 12-foot thick layer, you would do it by breaking it up into small segments of, say, 2 feet apiece or 3 feet or something like that. And the reason you would do that is because if you remember correctly, the stress dissipation is not strictly a linear function. It can be estimated that way, and we're going to do that. But for the most part, the stresses are very high, very close to the bottom of the foundation, and they drop off rapidly. And so if you just pick a spot in the middle of a very thick footing like this, that close to the foundation, then you may underestimate the settlement. So for the purposes of doing settlement analysis, normally you would break this into smaller pieces, but we're just going to do it all in one layer. And the calculations are the same. It's just that instead of it being 12 feet thick, it would be 2 feet or 1 foot thick or something like that, as you'll see. All right, so the bearing pressure is 150 tons times 2,000 divided by 10 foot square, or 3,000 pounds per square foot. And the question is, what's its stress change in the middle of this clay layer? Well, we're going to estimate our stress change through this 10 by 10 footing as using the linear interpolation of B plus Z times L plus Z, which, remember, that was based on the assumption that on each side of the foundation, the stress propagates outward and downward at about a 1/2 to 1 slope. And so as you go down 1 foot, the area gets wider by a foot, okay? So 150 tons times 2,000 pounds per square foot divided by 10 plus 11, 11 being the depth Z in the ground, which is 5 feet plus half of 12, which is 6. So we end up with 680 pounds per square foot stress change at the middle of this this clay layer due to the load applied up here by the foundation, okay? All right, now let's calculate some other things. We're not given everything we need to know, so we do have all the values. These are right off a chart like DM7, which basically says void ratio is equal to the moisture content times the specific gravity divided by the degree of saturation. We were given all those values, so we can calculate our void ratio in situ as 1.404, pretty good size void ratio. We need to calculate the unit weight of the clay. So the saturated unit weight of the clay is going to be equal to the specific gravity plus the void ratio times unit weight of water divided by 1 plus the void ratio. So we find that our saturated unit weight of the soil is 106.5 pounds per cubic foot. All right, so now calculate the effective stress at the mid-height of the clay layer. All right, so the effective stress is equal to the total stress minus the pore water pressure. So the total stress is 4 times 118, which is the weight of the sand up here, plus 5 times 124, which is the weight of that sand below the footing, plus 6 times 106.5, which is the weight of the clay down to the mid-height of the layer, okay? And that 106.5 is what we just calculated, and that's the saturated unit weight of the clay. Then we're going to subtract, since we're getting minus pore pressure, we're going to subtract 11 feet, which is groundwater tables right there. So it's 5 feet plus half of 12, that's 6 feet. That's a total of 11 times 62.4. So the initial stress in the mid-height of the layer is 1,045 pounds per square foot. Okay. Now we're not given an E log P plot. The only thing we're given is the liquid limit. So we have to estimate our C sub C based on the liquid limit using Skimpton's relationship. It's 0.009 times 64 minus 10. So it's 0.49. This is a relationship we looked at a few minutes ago. We now have all these values. We know our initial void ratio. We know our initial stress state. That was a 680. We know our initial stress state was 1,045. We know our change in stress, which was the 680. Just plug all those values in, and it basically says that 12-foot thick clay layer is going to settle, keeping our units straight. 12 feet is the height of the layer. Keeping our units straight, that clay layer is going to settle 0.53 feet or 6.4 inches based on the load that's applied by that footing. Okay, that's a really, really high amount of settlement. Hopefully not something that we've designed, but that's how you do the calculation. And again, the only thing I remind you, this is how you do the calculation based on the estimate of the settlement in the entire 12-foot layer in just one big block. You would never do that in practice. For the purpose of the exam, they would give you either a smaller zone or ask you to calculate it in the top 2 feet or some such thing. But just in practice, you don't want to do a real thick layer, especially that close to the bottom of the footing, because you're going to underestimate settlement. Okay? All right, got some questions here, Brian. In the bearing pressure, where did 2,000 come from? 2,000 is the conversion from tons to pounds, okay? 150 tons. Got to pay attention to how these, and I'm changing these around so you'll get used to the idea that they're going to ask the questions a lot of different ways. So 150 tons times 2,000 pounds per ton, okay? All right, can you explain how 11 was derived for Z? Yeah, sure. 11 is, we're coming off the bottom of the footing, and so we're going to the mid-height of the 12-foot thick layer, so half of 12 is 6, and then from the top of the clay layer to the bottom of the footing is 5, so 5 plus 6 is 11. Okay, good question. Don't want to lose anybody. All right, now, let's do this with an E log P. Rather than C sub C, let's just say they give us an E log P. So they give us this nice curve. So we've already calculated our initial stress is 1,045. We go in here at about 1,045. We go up, hit the E log P curve. We slide across, and we read the value. It's slightly less than 1.4. So just because of our really incredibly good eyesight, we can interpolate that out to 3 places. So we estimate our initial void ratio is 1.395. Now, that clearly would give you a scale better than that, but you get the idea. Our change in stress is 680. If we add that to our initial stress, that's a total stress of 1725. We come in here at this really great chart scale, and we see that that's about 1725. Again, they're going to give you a better scale than that. Come up, hit the point on the E log P, rotate across, and we're going to read that final void ratio as 1.288. Okay, then we just plug that into the other settlement equation, which says the change in the height of the layer, H, is equal to H times the change in the void ratio divided by 1 plus the initial void ratio. So we just plug those values in, and look at that, we get exactly the same values. Okay, so you can work the problem either way. All right, now there's one more thing we can do with consolidation that can be a great source of questions on the exam, and good thing to know, and that's consider the time rate of consolidation of clay. And the theory shows that there's this time factor, T sub V, that's a function of a consolidation or compression index, C sub V, times the amount of time that we feel like waiting. And that then is divided by this h, height squared. Now, be very, very careful. Make yourself a set of notes about this. In this particular case, when we're talking about time rate of consolidation as opposed to magnitude of consolidation, magnitude of consolidation is the amount of settlement you're going to get, and that is what we've been calculating so far. What we're getting ready to talk about now is time rate of consolidation. And this illustration here shows that if we have a soil zone and we have drainage in the top and the drainage in the bottom, that the closer we are to these edges, the higher the degree of consolidation that has occurred. But out here in the middle somewhere, the degree of consolidation, because the water has further to travel, the degree of consolidation is much less, okay? So if you pick some spot in here and I say, okay, I want 70% consolidation, and you would just go up through here and look at these degrees of consolidation for 70%, you'd see that the average value in that 70% zone would be something like that. They're saying it's 0.403, okay? But that's based on the soil being able to drain both top and bottom, okay? And that's the significance here. H is not the thickness of the zone we're talking about. H is the maximum distance to drainage. So if it's drained both top and bottom, the maximum distance to drainage is half of that distance, okay? So it's half of that distance. If there's drainage on only one side, let's just say the bottom of the specimen or the bottom of the layer is impermeable and all the drainage has to go out the top, then H is the full thickness of that layer. So for the purposes of time rate of consolidation, H, or the thickness that we're talking about, is not truly the thickness, the layer thickness. It is the maximum distance to drainage. All right, so let's just see how this would work. Have the same soil situation here, and the question is, how long would it take to achieve 70% consolidation? Well, we know if we want 70% consolidation, then our time factor, T sub V, is 0.403, which is what we talked about. We see our consolidation coefficient is given to us as 0.01 square feet per day. And so really it's just plug and chug. We resolve the equation for time. That's what we were asked. Time factor T sub V we were given off the chart, 0.403. In this particular case, we have sand above the clay. We are told that it's porous rock below the clay, so we can conclude that we have drainage top and bottom. The layer thickness is H, so the maximum distance to drainage is half of H. It can go out the bottom, it can go out the top. So it's the thickness of the layer, H divided by 2. So it's 12 divided by 2, divide that by our consolidation coefficient, and it ends up telling us 1,450.8 days, or about 4 years, okay? All right, so just remember, for the purpose of the time rate, H is maximum distance to drainage. All right, coming down to the wire here. Last thing we're going to talk about is slope failure. Now, if you've done much slope failure work in your careers, you know that there's some complexity to it. So for the purpose of the exam, they just can't give you something where you have to go through and find the maximum critical slope, and you're going to do 50 iterations or some such thing. You just don't have the ability to do that because you don't have the time. So they're going to have to define it down to the point where you can do something fairly rapidly. But they can ask you a lot of things about it, or they can give you several different examples to work with. And so one of the techniques that we can use is that we can simplify it to the point where it's definable, which is what these charts typically do. And there's dozens and dozens of these charts out there. Some of them have water, some of them have different types of soil, phi and C, some of them have all manner of different assumptions. So again, go through your references and just make sure you know which ones you're going to use. And this is a very typical one here. It's a circular failure, so that means it's a cohesive type soil. It's homogeneous. There's no surcharge. There's no tension cracks up here at the top from desiccation or stress. Phi is equal to 0, so it means it's only a cohesion only. We're assuming it's a circular arc failure, which for a cohesive soil is almost close to correct. And then there's no water on the slope because that would really complicate things. Okay, those are simplifying assumptions. So here's the problem that we're given. We have slope of which is a 2-to-1 slope, which is 27 degrees off the horizontal, and the embankment or the slope height is 25 degrees. We have a total unit weight, which means moist unit weight, of 100 pounds per cubic foot. The shear strength of the soil we're given as 650 pounds per square foot cohesion. Friction is equal to 0. There's one other piece of information we're given, which is the depth from the toe of the slope down to some hard layer is 15. Now, why do we need to know that? Well, the flatter the slope is, the more likely it is you're going to have a base failure, okay? The steeper the slope is, the more likely you're going to have either a slope or a toe failure. But for a real flat slope, the failure can plunge down some significant depth. And so depending upon the height of the layer, the height of the slope, that plunging can go down some considerable depth. So for the purpose of this chart, they want to look at this ratio between the height of the slope and the depth down to some hard layer to make sure there's not some constricting layer there that's going to control how deep the thing can plunge. So that's why they're asking you that. All right. So this coefficient, little d, is the depth from the toe down to the hard layer divided by the height of the embankment, which in our case is 0.6. And then we're going to calculate the factor of safety of the slope based on the stability number, which we're going to get off the chart, times the cohesion, and we're going to then divide that by the unit weight of the soil times the height of the soil. So this is kind of the driving force part here. All right, so how do we do this? So we go into our slope, which we said is 2-to-1, which turns out to be about 27 degrees. We can go in either way. And we slide up into the chart until we get into the little D zone in here, which was about 0.6. And then we just simply slide across until we get to 6.2. Now notice that the chart tells us these are circle failures up here where the failure is occurring up within the embankment itself. That's a toe failure, which is kind of the most optimum condition. And then we have a base failure. So in the little D zone that we're in, and for the height of the embankment, we have the ability to have a base failure. So that's what they're predicting would happen. All right, so we take our stability number, 6.2, and we just plug it into the equation. Factor of safety then is 6.2 times cohesion. We were given that. Unit weight of the soil, 100. Height of the embankment, 25. So we got a factor of safety of 1.6. So not too bad, actually pretty good, especially for a dry slope. All right, that's the program for this afternoon. I've got a couple questions here. There's my email address. If you start looking at these things and you have questions and we don't have time to get to them all, by all means send me an email and I'll be glad to address them if I can. I always get a few questions along the way because everybody sees these things in a little bit different way. All right, Josh, let's see. For those of us taking the geotech depth, can you give us an idea of what types of topics we can expect? Yeah, well, you certainly need to go into that website that I mentioned to you, but liquefaction issues on seismic loadings, you probably want to look at Schmertmann's method for settlement of sands as opposed to the settlement of clays. There's a lot of topics on seismic loading and site class calculations, just much more in-depth analysis of some of the foundation types. So look at that website, and I think you'll get a lot better handle on it. But those are some of the things, the seismic and liquefaction and code issues there you need to really address. All right, let's see. In addition, what is covered? Yeah, okay, I got that, I think. Jeremy, do you know offhand your source for the slope stability charts? Let me look at that. I can probably tell you. I think that's a DM7 derivation. I'm pretty sure that's where that one came from. If you can't find it, send me a note, and I'll be glad to go back and look. But this same chart, believe it or not, is probably in a couple different sources. But I'm just based on the print on this. I'm almost certain that's a DM7 derivation. Okay, if you got any more questions, we've got just a couple minutes here by my watch, and we'll try to get to them real quick. Again, if not, the main thing here is just develop a discipline to work through these problems. There's a lot of material, obviously, and the more times you go through it, the more comfortable you're going to be, and you got to be efficient to get these problems done in the time frame that you have. So just work those problems. And again, keep my email address handy. So if a month from now or whenever you're working on it, or whenever you have time, if later on you have a problem, send me an email. I'll be glad to help you if I can. Okay, quick question here. Would a drilled shaft have side frictions? Well, surely. Everything's got side. If it has shear strength and you're pushing on it, it's going to have resistance, right? So absolutely, you're going to have side shear in a drilled shaft. Just going to be less than in a displacement pile. Okay. Well, thank you very much for joining us this afternoon. Been great involvement and great questions. And if you have any more, send them to me, and I'll be glad to help. And good luck on your studies and preparations for the exam.